understanding. They made small errors, but, yeah.
When in regards to the, I assume it's the MATLAB assignment that you created, it just
Yeah.
says assignment. How is that gonna calculate into the final grade? Because right now it's just,
I think it's on the syllabus, if you look, I'm not sure if it's 5 or 10%, something like that.
I mean, the bonus MATLAB. the one
Oh,
we turned in
that's
couple
like a
weeks ago.
quiz form. So what I normally do is drop the lowest quiz, and then I average out the scores of the best of the remainder. That's what I do, assuming you have this. I'll get that back to you, by the way. I've got that upstairs, I was sitting on it. And I'm sorry, I can't get that back to you soon. So today, I gave you homework on using the rotated Smith chart for impedance matching. And there are 3 basic things that can happen. Either the normalized value ZL can fall inside the one circle, or it can fall inside the rotated one circle, or it can be outside either. If it's inside the one circle, just to review, and this is going to be something you'll see either probably on the next quiz and final. If it's inside the rotated one circle, you have to go to the Y domain, go from Z to Y, then you're inside the rotated one, and then you choose whether you go to the top or bottom point by adding an inductive or a capacitive element. Then you go back to the impedance domain, and you add a series impedance that will negate the remaining J term. So if you're inside the rotated, you gotta go to the Y domain. If you're inside the rotated circle, you add a series of impedance, usually a J, an inductor, to get to the rim of the rotated circle. Then you go to the admittance domain and add a shunt element. And if you're outside of either, you can do anything. Basically, you can add either series or shunt first, and the other one next to get to the actual center of the circle. Or we've got 2 others. Anybody else? Nobody else. You can choose. All right. So I want to do at least a couple of these because in doing them, you can see usually questions are answered. A lot of times I've found out, especially with graduate coursework, you don't even know where to begin to ask a question about a way problem stated. And it's really true in things like random signals and systems. Have you guys had random yet? All right, well, you know, that course, especially gets real hairy when it comes to the conditional probabilities or joint probability densities. All right, so which problem are we doing?
10.12.
10.12, all right, man. Go ahead.
A matching network consists of a length of a T-line through section in series with a capacitor. Determine the length and wavelengths required of the through section.
Is it capacitor in series with it or parallel?
In series with a capacitor.
Okay. And they got a load here, right?
Yeah. Determine the length and wavelengths required of the through section and the capacitor value needed to match a 10 minus J35 ohms load impedance to the 50 ohm line.
Okay. This is one where it's you gotta think about this first. So I'm gonna go ahead and I'm gonna first draw just a regular Smith chart. Use this one here. So our first thing is normalize it. Normalize it, you have 10, we're gonna say, ZL normalized is 10 minus J35 divided by 50. This is small, so this is gonna be, this boils down to what? 0.2 minus J, what is that? 0.7, right? Okay. So we gotta find that spot. Minus J.7, this would be minus J1, minus J 0.7 is somewhere down here, if you look at the trajectory. And then 0.2 is fairly, it's a large circle, about like that. So there's gonna be the first point, ZL, right here. Y'all with me on this, class? Now, if you think about this, our goal is to get back to the center. So if I take a straight, I'm gonna first do this. We're gonna figure out what domain we're gonna do. If I look here, I'm gonna get a number of wavelengths towards generator right here. And if you can give me that, that'd be helpful. So if you got a Smith chart, get it out and do this, and we'll all see how this works.
Oh,
0.4, did you say?
Yeah.
All right. So it's 0.4 lambda. I don't know what the solutions have. That's our starting point. Now you need a compass to do this one. So you're going to go ahead and take this, and you're going to move. Well, first we'll circle. I'll make it in red. This is a circle of constant radius. Trying to be like that. And we're going to move to this point right here. We're at the one circle. So this is the first point. Now the reason I know I can do that is if you look, we take the trajectory, we're in the impeached domain, we're going to come up and intersect that spot. You all see that? That's going to have a normalized impedance. It's got a real value of 1 plus J something. You all see that, class? All right. We're not going to the impedance domain in this one. It wouldn't work. Because we're not going to put anything in shunt. So then, when you get that point, then you take your straight edge, draw a line through there, and then we're going to get a second, this would be 0.2 wavelengths towards generator. And what's the value at that point, by the way? This value right here is that value, 0.2 minus J 0.7. But what's the value right here where it intersects? It's 1 plus J something.
J 2.4.
1 plus J 2.4, do we agree on that? I want to make sure we get a consensus here. Yeah. All right, 1 plus J 2.4. All right, now give me the distance right there.
195 lambda.
Check it. This is 0.095?
195.
195 lambda. Okay. Does that, anybody confirm that?
Yeah.
I'll let everybody catch up. I want to make sure you see, and you're just getting your drawing instruments out, but I want to make sure you see this one, because this one's a blend. It's not just with elements, and it's not just with transmission lines. It's a blend, so it's important to see this. And I can tell you one other thing about this. These kind of problems require you to really understand this. If you don't, you won't see through these things so easily. While you're doing that, I'm getting this quiz back. All right, are we good? You got it, Chris.
Yeah, I'm following along.
Do you have a Smith chart? Or?
I can't move my neck, so I figured I would just go and watch. So I woke up.
Good. I've got a problem that way too. Right back here, I've got a torn rhombus muscle. It's below the trapezius. And sometimes it's stiffened, it'll go into like a spasm. My neck just hurts like crazy. So if you see me not bending my neck, that's what's going on. All right, we ready? You got it? Okay. Now, after that, you can see I've got 1 plus J 1.4. When I look at this capacitor right here, the capacitor has a capacity reactance of minus J over omega C. Y'all agree with that? Remember, this is the impedance domain, so now we have to normalize that value. We have to divide it by Z naught. You follow the logic on this one? Divide it by Z naught. And that has to negate this J 2.4, right? Y'all with me? Because that way, when I add that, which is gonna have a value of minus J 2.4 to this, it gets rid of that, and then you just have one, and we're back at the center where we need to be. So the value of that capacitor, I'll put it this way, it's minus J over omega times C times Z naught has to be equal to really minus J 2.4. And that means when I look at this, I have really I'm gonna say this, I'm gonna say C will be equal to 1 over 2.4 times omega. And so it's 1 over 2.4, and omega is 2 pi times F, and what's the frequency? Is it a gig?
Yeah, 1 gig.
All right, so times 10 to the 9. And you can tell me what that is.
You can use the Z naught too.
Yeah, I'm sorry. My bad. You know, it's what? 50. So 50, my bad. You're right.
1.32 picofarad.
Is that right, guys? It sounds right. You got that? Anybody else? All right, I'm gonna believe it. I don't know what the answer is, but that's how you do that problem. Now, hear me on this one, so you can understand. If they said they didn't want a capacitor there, but they wanted an inductor, all right? So just think about this. Now I want L. Now L has a value of plus J something, right? Not minus. So now I wouldn't end up here. Oh, I didn't get the distance, by the way. The distance for that one is going to be 0.9 or 0.195, the actual length of that stub, or LT, I guess it's through line, is going to be 0.195 lambda minus, and it started there at 0.4 lambda. You have to add 0.5 because it's going to be negative. And you can give me that answer too. I'm sorry, I didn't get that down.
295. 0.295 lambda.
0.295 lambda. So that would be the length of the through line for the capacitor. I got ahead of myself. I'm sorry. That would be the answer to this problem right here. The value of C would be 1.32 picofarads, and L is 0.295 lambda. Does that agree with the book's answer? Okay, anybody?
We didn't have solutions.
I didn't put the solutions up. Oh man. Well, send me an email and I'll put it up for chapter 10. I try to make sure all the solutions are available to you. It's helpful to look. Don't look at it first. Struggle with the problems, learn how to think about it, but just look at that and confirm your answers. I'm going to bet it is, but I'll make sure I put up the solutions. But that's the technique. Now, here's what I wanted to show you. What if I said I didn't want a capacitor to do this? I wanted a series inductor. You with me on this? An inductor has a value of plus J omega L. Normalized would be plus J omega L by Z naught. Follow me? Now, I wouldn't move to this point. I'd move to this point, right here. You all follow me on that? It's going to have the same value of real. It's 1, but it would be minus J 2.4. Follow me? Now, the reason it's I want to go to minus is that minus J 2.4. I can add a plus J, whatever this is going to be. It'll be J omega L divided by Z naught, and I'll just say J omega L over Z naught is plus 2.4, correct? Now I'm going to have to go further. I'm going to have to go to a point, or if I draw a straight line down here, I don't know what the wavelengths towards generator on that one is, but it'll be different. I wanna do this part, because this is the kind of stuff you're gonna see in the final exam. If you know how to think about these problems and understand them, this will come natural, but whenever, you know, you try to cram all this stuff in and you haven't really looked at it before the final, it gets really confusing.
Like, what, 305 lambda? About.
Yeah, that's right, this is 0.25, it's about 0.0. Now, here's how I get the distance. I know if I go all the way around, that's 0.5 lambda, correct? So I can say, well, what I'll do, maybe I should, all right, I'll do it the other way. To get this distance that we go from here all the way, we start here, we go all the way around to here. This would be my second L, LT for the inductor too. This is for an inductor. That would be equal to 0.305 lambda minus 0.4 lambda. And then I'd add 0.5 lambda. And what's that value going to be? About 0.4, is that right?
0.405.
All right, 0.405 lambda. Now let's get the value of the inductor too right here. So now I have omega L over Z naught would be equal to 2.4. I've got rid of the J's. I know they're gonna cancel. Y'all, can everybody follow me what I'm doing here? Then I'm gonna multiply 2.4 by Z naught, or by 50. And I'm gonna divide by omega, which is 2 pi times 10 to the 9. And that would be my value of inductance. I've got one more comment on this. You know how to do it this way. Can you give me that? Man,
It's 19.8 nano henries.
sounds right. Now, the reason a lot of people use inductors in series is because a lot of the times the loads you're driving require a DC bias. An inductor has 0 ohms of resistance to DC, theoretically, all right? So they like inductors when you are doing matching. Preferably, you put inductors in series if you're going to use them, if you have a choice, and capacitors in parallel. Inductors in parallel are really bad because they short out any DC biasing. You want preferably a capacitor in parallel and an inductor in series if at all possible. Just keep that in mind when you're doing this. In the real world, you're going to find out the hard way, oftentimes when you smoke a transistor or something a couple times, that this is the preferred way to do it. Of course, you would probably destroy an inductor more likely. Okay, so that's that problem. I'm sorry I didn't put up the answers for the solutions. Now, next problem, I want to do at least 1 or 2 more, because these are real important. Just let me know, how many tried these things? 1? Okay, well, you're honest. Y'all follow me on this one? All right, let's do this one. I want to hear from you how you would do it. You might as well pick the next one in the series.
Is the quiz this Friday or is it next Monday? I've heard both.
I think I might do one catch-all on Monday, and that will also serve as a makeup for anybody. Okay. And I'm not sure. Actually, I prefer to do just one more because I want to try to finish up this microwave stuff without really burning too much class time on quizzes. So go ahead with the next.
Design an L section matching network to match a 10 plus J.
Which number is this?
2.13.
Okay. Go ahead. Z on this one.
10 plus J 15.
Oh, I hate these. These are small.
Z naught is 50.
so this is C naught equal 50. All right, I'm gonna need your, how do we do this? What's the very first step? And I'll draw what you're thinking about. Try to draw this switch. Really looking for something that's dark. All right. So. The best, but we're gonna just use it for that. That's R1, and here's the rotating switch. And that's probably the best. So first thing, what do we have to do? Very first thing you always do,
Normalize the,
find and normalize the beats. That's always the first step. So ZL here is gonna be 10 plus J15 divided by 50. So that's 0.2 plus J 0.3. Boy, that looks like it's just inside this circle. So 0.2 is somewhere out here, and J.3 is like here, I think. You correct me if I'm wrong. And this would be 0.1. Is that right, class?
that's right.
I'll let everybody draw it and catch it. Now, here's a comment I have. That's inside the rotated circle, right? So that means our first element's gonna be an impedance element. Follow me? If you use an inductor, you're adding plus J. If you use an inductor, you're gonna hit up here. We'll figure out the amount in a second. If you use a capacitor in its impedance, then you're gonna hit down here. So there's a decision you have to make. Does he qualify? Does he say any conditions? Let the series element be an inductor in? He should, because it should be. He doesn't? I mean, there are several solutions. You can go with a capacitor in series first and an inductor in parallel, or an inductor first and a capacitor. Preferably the inductor in series and capacitor in parallel is the best solution if you're given that option. The capacitor doesn't have any problems at DC. It will not allow current to pass, so you don't short it out and cross the load. And an inductor won't block DC. That's one of the key concerns. So for this one, we're gonna go, and you're gonna have to use the point 2 trajectory is right here, roughly. If you go from here to here, where's the intersection point? That's point 1, that's point 2. What value is that?
0.2 plus J.4.
0.2 plus J 0.4. Can you guys confirm that? All right. You can see I'm adding, I started at 0.3 J. I'm going to add enough to get to 0.4, which is 0.1 J. You with me on that, everyone? So the differential here is going to be 0.1 J that I have to add. So when I look at this, the first element is going to be an inductor, and it's going to be an inductor L. And to get this value, we look at the inductive reactance here, and that's J omega L, but we have to normalize it by Z naught, and that has to equal J 0.1. Now, do y'all follow the rationale on that? I'm adding an inductor to increase the J, the real part, the J value to be acceptable, 0.1. Y'all agree with that? Now we got to calculate the value. I'm going to calculate the value of L right now, if you don't mind. And so to get L, what do I do? Well, I say L for this one is going to be equal to 0.1 times Z naught, right? And then it's divided by omega. And that's 0.1 times 50 over omega is 2 pi. Is this at a gigahertz still?
Yes.
All right, times 10 to the 9th, so you can give me that value.
.7 nanohenries, 0.79.
0.79 nanohenries, is that about that, guys?
Yeah.
You follow me what I'm doing here? All right, now we're at this point. This is point 2. What do we do next? Take 1 over that value. Take 1 over 0.2 plus j.4, or you can just take your straight edge. Go right through the center until it intercepts at the conjugate point here. And this is going to be the y value, or it will be y equals 1 over 0.2 plus j 0.4. And it better have a real part of about 1. And it's going to be minus j something. You could just take 0.2, 1 over 0.2 plus j.4.
1 minus 2.
J2? That's nice. I like doing that. Now that's admittance, right? We're in shunt, so just think about this. Is everybody following me on this, how I'm doing? If you have any questions, please ask. The whole idea is to make sure at the end of the day, you only have a real part of 1, no imaginary part. It doesn't matter if it's admittance or impedance domain. Once you have that, you're at the center of that circle, the reflection coefficient is 0. All right, now what do? We're in the admittance domain, right? We gotta get rid of this. What do? Capacitor and parallel, right? If we look at this, we're gonna put a capacitor and parallel right here. So, and the order that they appear is important. You can't put the capacitor first. So for this one, the capacitive reactance is 1 over j omega c. If I normalize that, it's 1 over j omega, or it's 1 over j omega c z naught. Admittance, the normalized admittance would be 1 over that. So I have an admittance here of j omega times c z naught. And that has to be equal to, in magnitude, plus j2, right? Because it's got, when added, it's got to kill that minus j.2. So this is going to be equal to j0, j is 2, pardon me, just 2, j2. Or we can say c is equal to 2 over, and this is going to be omega z naught. Omega is 2 pi 10 to the 9th, because it's a gigahertz, and z naught is 50. So you can tell me what this is. I think it's picofarad, but I might be wrong.
6.37 picofarads.
But pretty close. Now, if that's the first solution to this, but once you catch up, I want to just discuss this with you so you can appreciate it. What if, what if you wanted to use a capacitor first in series and an inductor in parallel? I'm waiting for it until everybody gets this down. Hold on. Okay. I don't want to go too fast, so I want to make sure you see it. Okay. Are we ready? Okay. So, what if all of a sudden be like 10 plus j15 and let z out is equal to 0.2 plus j0. We're going to leave that up there so I can use this. But now this is still 0.1, but what I want to do is put a capacitor in series. Bad idea, but I'm going to do it. And then it'll be an inductor in parallel. So if I wanted to put a capacitor in series, it's impedance, right? Where would I go? I'd start here. This would be my first point still. And where am I going to move to? Yeah, it's going to be this. And this is going to be what? 0.2 minus J 0.4, correct? Take a good look. Can you see it? It's really just the trajectory point 2. You're gonna be on the real part of point 2, and it's always gonna intersect either plus J.4 here, or on the rim minus J.4. So this is the point. Now, how much did I actually subtract from the value? I started at point 3, right? See that J.3 here? And I ended at minus J.4. That's subtracting minus J.7. Do you all agree with that? So from here to here, that's minus J 0.7. So that means this capacitor right here, it has a capacitive reactance minus J over omega C, and then normalized by Z naught, correct? Everybody follow? That has to be equal to minus J.7 equal to minus J 0.7, or we can say what? The value of the capacitor would be equal to 1 over 0.7, right? Times 2 pi times 10 to the 9th times Z naught of 50. And what's that value gonna be? This is the second solution, what I'll call the bad solution.
4.55 picograms.
Anybody confirm that? Okay. All right, follow me on this? Now, I'm here. Now I go to the conjugate point, which is gonna be right to the center, or 1 over that value. And this is gonna be 1, you do it if you want, but this is gonna be 1 plus J2, right? It's gonna mirror this value. So that was point 1, this was point 2, this would be point 3. And then what do? I gotta get rid of that J2, right? But I'm in the admittance domain, right? Y'all follow me? So in the admittance domain, I need a minus J.2, correct? Look at this. So with an inductor, the impedance of inductor is J omega L. Normalized impedance is by Z naught. So that would be really the normalized impedance of that. 1 over that would be the admittance. Or I would have Z naught over omega L minus J would be equal to minus J2. I need a minus J2 because that's plus J2. So I'm going to get rid of these minus J's. And then you can see that L itself would be what? L would be equal to Z naught over 2 pi, right, times 10 to the 9th, right? And then it's going to be divided by 2. And can you give me that? And that's 50. Z naught's 50. I'll get out of here.
3.98 nanohenries.
3.98? Follow me? This one was something where I gave both solutions just so you could see it clearly. And I want to make sure you understand, for a problem like this, you can always have a capacitor or inductor first. But if you use an inductor, the second one's going to be a capacitor, right? If you're inside a rotated circle, in either rotated circle. Whatever element you use first, the next element will be the opposite. It's capacitor first, inductor second. Now, if you're outside both, all bets are up. You can use 2 capacitors, 2 inductors. And it's because of the nature of the problem. All right. Any questions before I move on to the next one? I hope this is helpful. Which one would you like to do? These are actually pretty good problems.
1.6, and I'm skipping a few.
Yeah, that's fine, which, we can do 1.6.
So suppose you want to match a 20 plus J50 ohm load to 50 ohm line.
Alright, so you got a ZL here. 20 plus J
50.
50.
And it
And
says,
you got a 50 ohm line?
yes. And it says for the design of an L section matching network, you notice that the normalized load impedance lies outside of both the +1 JX and rotated JX. Find all 4 possible solutions.
No, we're not gonna find all.
And for each
We're gonna
one,
find
determine
some.
specific values. And it's 2.4 gigahertz is the frequency.
Alright, so. Let me try to do my Smith chart thing here. Something like that, not exactly on the scale. Okay. So, first thing we do is what? Always. Normalized impedance, so that's 20 plus J50, right, over 50. So that's gonna be 0.4 plus J1, unless I'm mistaken. Y'all agree with that? All right, so find that point. Well, J1 is right here. It's this trajectory right here. That's J1, and if you look at 0.4, it's gonna be about here. I think this would be the first point, ZL, we'll confirm that. 0.4 plus J1, is that right, class? About there. Now, here's the question. Do you want to add a series element first, or do you want a shunt element? We're gonna discuss this once you write this down. And take a moment to think about this, how you would approach this problem. Remember, you're in the impedance domain, and if you look, this would be the 0.4, sorry, 0.4 value of real part. This would be the trajectory. You all see this? Now, I'll let you all write and think about it. If you were faced with this problem, and say you wanted a series impedance element to do the matching. So, if I have a series impedance, I know I'm gonna be on the 0.4 trajectory. I can't change that, but I would like to change the value of J to get down to that point. You all see that? I would like to go from here to here, where it intercepts the 1, and it would be plus J something. Now, I don't know what that is, but if you just trace along the 0.4 circle until you hit the 1 circle, and it's gonna be 1 plus J something. If you can tell me what that J is, and it's gonna be like 2.4, maybe 2.5, I can't really tell. Maybe more than that. now that I think about it.
It's much more.
What is it?
It's a lot more, I think.
A
I
lot?
don't think it allows us to see it.
He goes all the way to the,
Yeah, it goes to
No, the 1.4 trajectory.
on this side, it runs all the way to.
Oh, I'm sorry. You can't get there. I'm bad. If you have a series of them, we're gonna have to go there. My bad. I did that. That's my fault. Can't go that way. You'll never hit it, because he's right. It's just gonna hit here. But we're gonna go from here. If we had a series element, we could go to here, or we could go to here. 2 possible points. And that's still in the impedance domain. Y'all follow me, class? We're gonna add a series impedance. So if we added a series impedance, we have J1, and if we keep going and hit here, there would be a certain amount of J that actually we'd subtract from it, not add. This would be less. And we could keep going and subtract even more and land here. So there's 2 possibles. I'm gonna go to the near one here. So this was J.4 plus J1. This point is what? Just look where 0.4 intersects the rotated circle.
0.4 plus J.5.
0.4 plus J 0.5. You confirm that, people? All right. That means I changed the value of the imaginary part from here to here. I have a delta of, I guess you'd call it x, equal to j 0.5, right? It was reduced by 0.5, correct? So that means I need a series element that would have a negative value of minus j 0.5. I'm gonna put that here first. This is an impedance. So it would be something here, it would be minus j 0.5. That's the normalized impedance. What does that have to be, class? Has to be a capacitor. So I'm going to show that. So now, for a capacitor, the impedance of the capacitor is minus j over omega c. Normalized, we have to divide it by z0. Correct, everybody? Remember, the whole idea is I have to go to either this circle, and I can't get there by adding impedance, or to this circle. One of the two, if I'm going to add a series of impedance. I can't get to this one, so I go to this one, and I could go to 2 points on here and here. And I chose the near point. So what's the value of that? I'll do it right here. For that capacitor, what's it going to be? It would be 1 over, and then it would be 0.5 right here. And it's going to be times omega, 2 pi times, and this is 2.4.
It's actually 2.5.
2.5
Yeah.
times 10 to the 9th. Times 10 to the 9th hertz. And then it's divided by Z0 as well, which was 50. So that would be my C1 here, and I'll call it C1. What's the value?
2.55 picofarads.
All right, if we went to the conjugate point here, this is 0.4 plus J.5, this will be 0.4 minus J.5. Y'all follow? So we'd have to add another, you would have to subtract off, not 0.5, but it'd be 1.5. All right, J 1.5 negative. You'll follow me? And that would give you a different value of capacitance. But either times, you're going to be adding capacitance to get to these 2 points. And so that's C1. I'm right here. That's the impedance domain. Now I go to the admittance domain. And what's the value? So that was 0.1. This is 0.2. This is going to be 0.3 here. And that's simply 1 over 0.4 plus J.5. 1 minus J something. What is that?
J 1.2.
Is it minus J 1.2?
Right.
Just pick it. I want to make sure everybody has a chance to confirm this.
Yeah, I got 1 minus j 1.2.
1.2 roughly. Okay? Now that's the admittance domain, right? We're in the Y domain. So now we have to add a shunt value that has a value of plus J. This would be a second capacitor. This is going to be C2. And if you think about it, that's admittance, right? All right, so when we think about capacitors and admittance for C2, well, that's the way I always do it. The impedance of a capacitor is minus J over omega C. Normalized would be minus J over omega C Z0. The admittance normalized is 1 over that, or it's J omega C Z0. That would be the admittance of this capacitor C2. And that has to be equal to 1.2. So it negates that 1.2 over there. This has to be equal to J 1.2. Or I can see the capacitance C2 would be equal to 1.2 over, and then it's going to be omega and Z0. 1.2 over 2 pi times 2.5 times 10 to the 9th. And then it's Z naught is 50. And you can give me that too, that's the second capacitor.
1.53 pico.
1.53 picofarads. Is that right? Y'all follow the way we're doing this now? Now remember, that was a series element first and a shunt element, both capacitors in this case. What if I went over here to the second point right here? The capacitor is going to change. The first capacitor in series, right? It's going to change. It's going to be larger in value. We can do that one. But then when I go to the conjugate point, it would be 1 plus J1.2, right? There we would have to add an inductor instead. With me? And we can, I'll show you the other solutions. Now, if you just think about this, we started with series, then shunt, 2 possible shunts, either a capacitor or an inductor, right? Well, if we started here and we go to the admittance domain, now I'm down here. Follow me? I'm in the admittance, and if I'm in the admittance domain, I can add in shunt until I get here or here. Y'all follow me? Then from there, I go to the impedance domain and I add in series and get back to here. That's the idea behind this. It takes a little time to appreciate the different possibilities. So I'm going to ask you, we worked one of these solutions and I talked about the other 3 that are possible. But go ahead and make sure you do that problem thoroughly. You'll be happy you did. You'll understand a lot about this when you're outside either the rotated or just standard one circle. I want to do one more of these, and somebody's got one that's a burning desire. I only did one of those solutions because these things can suck up a lot of time when you're outside either of those circles. Just because there's so many possible solutions.
Two other ones that are interesting.
Okay, let's see if we could work together, we might be able to nail them both. Which one?
There's one that says, suppose you want to match a 100 ohm line to a load of ZL equals 200
Which
minus.
number is this?
10.17.
All right, hold on. So I got a 100 ohm line. Go ahead.
It says, suppose you want to a ZL of 200 minus J100.
Here's my CL.
It says a
200
resistor.
minus J100?
Yeah. It says a resistor in series with a capacitor next to that parallel. In parentheses, it says that that's what that represents.
Well, that doesn't, go ahead.
And then it's 500 megahertz. It wants you to determine the element values for the load.
500 meg?
Yes.
All right.
And it says design a shorted shunt stub matching network, and then design an L section matching network.
We're gonna do the L section.
So
Sure,
not the
he wants a stub tuning, I'm sorry, he wants transmission line tuning on that one, is that what he said?
The shunt.
Don't worry about that, let's do it with the L section. You know how to do, you've done transmission lines with stub tuning, right, both series and shunt. So we're gonna do it using standard L section. Does he have any specification about any conditions about DC bias or anything? What he does?
No, on this one.
All right, so let's go ahead and do it. First, as always, we gotta get normalized ZL, right? That's ZL over Z naught. And for this one, it's at 100, right? So it's 2 minus J1. That's inside the rotated, or inside the one circle. So let me draw a little Smith chart here. this is the article 1 circle, and I have 2 minus J1. So the 2 circle is about here, something like that. And minus J1 is gonna be, there's minus J1, so it's gonna be about here. This is gonna be 0.1, which is CL equals 2 minus J1. And y'all follow me? That would be your first point. It's gonna be 2 minus J1. Y'all see it? Now, that's inside the rotated circle, so no matter what we add, if you think about this, when I'm adding the imaginary parts, the only thing I can do is change the location on this R equal 2 circle. If I add in series, J, right? No matter what I do there, I'm never gonna get to the rim. That's where I wanna be. So I have to go to the admittance domain. So now I take 1 over that. This would be 0.2. And what is that value?
Which value do you want?
1 over, I take just 2 minus J1, 1 over that. I want the
0.4 plus J.2.
0.4 plus J 0.2. Follow me? All right. Now, that 0.4 is the real part of that admittance. Think about it right there. So I can either go, we're in the admittance domain. If I add capacitance, I can go, in parallel, I can get to this point. If I add inductance in parallel, I can get to this point. You agree with that? I prefer to put capacitance in parallel. I don't like inductance in parallel. It shorts out DC, it does, and there's other things that can go wrong too. So I'm gonna add a capacitance. So now, find the point where 0.4, that trajectory intersects the rotated circle. This is 0.2.
J 0.5.
This is gonna be 0.4 plus J 0.5, is that right? That would be the third point. Y'all follow me what I'm doing? So that means I added a net 1. I had to add plus J 0.3, right? It was at J.2 here. Now I had to get to J.5, so I have to add this much in shunt. Do y'all agree with me? All right. So now I have a capacitor. I know I'm gonna have a capacitor here. And the capacitive, if I think about this, the impedance of a capacitor is 1 over J omega C. Normalized, it's 1 over J omega C Z naught. The admittance is 1 over that, so it's J omega C Z naught for the admittance of this. So J omega C Z naught has to be equal to J.3. 0.3. Or I can see C is equal to 0.3 over 2 pi times 500 megahertz, or 5 times 10 to the 8, Z naught, which is 100. So what's that value? This is actually the first problems we talked about were inside the rotated.
0.955 picofarads.
And just to make sure everybody sees this, you could also add an inductance and get down to this point. All right, but I would rather not. So that's, because it's given a choice, always use a capacitor. Don't use an inductance. That's sort of the rule of thumb I look at. All right, now I'm at that point. Now what happens, guys? I went from here to here. This is admittance, then to here. What's my next shot? What's the next step?
You go back to the bottom.
Now I have to go and get I gotta go to the impedance domain, right? I'm gonna go 1 over that value. So I'll go one over that, and I'm gonna hit the rim, and it better have a real value of 1. That's gonna be 4th point. And that means my Y value here will be 1 minus J something.
1.2.
1 minus J, 1.2.
Yes.
This looks familiar. So now I need an impedance element to get rid of this minus J 1.2. So I need an impedance to have a normalized value of plus J 1.2. That's an inductor, right? You all with me, guys? So if it's an inductor, I gotta find the value of that. So an inductor has an impedance of J omega L. If it's normalized, I divide by Z naught. And I've gotta set that equal to J 1.2. And now you can see that L is gonna be equal to 1.2 times Z naught, which is 100 in this case. And it's divided by omega, which is 2 pi times 5 times 10 to the 8th, 500 megahertz. So that's L.
38.2 nanometers.
With me on that? How many see this? I wanna make sure I'm good. Y'all with me? I mean, if you have a question, Matthew, just ask away, because I wanna make absolutely certain there's nothing hidden, nothing you don't understand. The technique, theoretically, if you just think about it, the whole goal is to get to the center of that circle by adding something. All right, and if we can add in series or shunt. If you're inside that one circle, no matter what you add in series, can't get you to the rim. All right, so you have to go to the admittance domain, and effectively, in the admittance domain, add and shunt until you get to the rotated circle's edges, and then go back to the impedance domain, and then you nullify whatever's left. That's it. Yep.
So you always start in the impedance domain, more or less.
You have
and then
to,
if you
because you
have to
realize
go to
that-
the admittance,
Yeah, but you start there and you see where you land. Once you're there, if you're inside this circle, gotta go to your admittance. It's gotta put something in parallel first. If you're inside this one, that's fine. Then you add impedance in series to get you. Then the next thing is, once you get to the rim of that, then you go to the admittance domain, see what admittance you have to add in shunt. And it's that way. And if you're outside either, who cares? You go, do whatever you want. You can add impedance, or you can go to the admittance domain right away and add admittance something in shunt, and you can do it. It doesn't matter either way, but preferably if you ever have a choice. Capacitors in parallel, inductors in series. All right, that's the way it's usually done. Is there, I'm almost afraid to ask this. Did you have one more?
yes, the 10.19. It
Alright, hold
gives
on.
you a capacitor value and a resistor value.
Resist, oh, that's just in a load though. It's gonna translate to it into ZL in a second, but we'll do it. All right,
So
go ahead.
it's an L section matching network. It has a load of 25 ohms, and then it has in series a 1.061 picofarad capacitor.
All right, so he's saying the load looks like this, 25 ohms, and he's got a capacitor, the value of C equals what?
1.061 picofarads.
61 picofarads,
Yes, sir.
and he wants to match that with what line? 50 or 100?
50.
50.
And it's
Else-
at 3 gigahertz.
What?
It's at 3 gigahertz.
F equals 3 gigahertz. All right, now this one's not a big deal. Only thing we're gonna do is find the capacitive reactance there and replace that with the capacitive reactance, so it becomes just the load with values, real and imaginary values. So the capacitive reactance of this is what? Well, it's minus J over omega which is 2 pi times 3 times 10 to the 9, times C, which is 1.01 or 061 times 10 to the minus 12. And what's that value?
Minus J50.
Is that right? That sounds like Whitworth's problem. He started with 50, he found the capacitor value from there. That would do that. So really our load is simply going to be equal to this whole thing right here. Is ZL is equal to 25 minus J50. That's what it is. So when we do this problem, first thing is find ZL. And that's capital ZL over Z0. You can look at this. 25 minus J50 over 50 is going to be 1/2, right, minus J1. Do y'all agree with me? All right, now, after that, you plot it. So 1/2 is 0.5, and it's about this trajectory, something close to that. This is R equals 0.5, real far. And minus J1 is down here. This is minus J1. So that means this point is about here. This would be 0.1, and this would be a ZL of 1/2 minus J1. Can you all follow that? I want to make sure you can see where that point lies. Remember, it's 1/2 minus J1, so you gotta locate that. Does everybody know how to locate these points on the swim chart? Class? Okay. I'm glad you're here. There's quite a few people missing today, but this is kind of important. This stuff, this gets confusing if you're not on point. Now, we're outside of both of those circles, right? So, I'm gonna make a comment. No matter what impedance I add that would go in this direction, I'll never hit the one circle. Y'all take a look at that and convince yourself of that. No matter what I add, if you go along that trajectory, you're never gonna hit this circle. So, if I'm adding impedance in series, I'm gonna be going this way, right? If you look at that value, it's minus J.1. These are gonna be smaller values, so minus J something. And it depends where you wanna hit on there. So I'll ask you, if I move along this line, this 0.5 line, down here, is this 0.5 minus J.4?
0.5 minus J.5.
0.5?
Yeah.
Is that what it is? Confirm that? Okay. And then there'll be a conjugate point up here, which will be 0.5 plus J0.5. Y'all see that? So if we're gonna add series impedances, those are the 2 points we have to hit, right? How about we hit this one? All right, just because it's further away. So we started here at 1 minus J1 in impedance, and we're gonna end up here at 0.5 plus J.5. That means I negate this, I have to add plus J1 plus J.5, or the net amount I have to add from here to here, I have to add plus J1.5. Y'all follow me how I got it? I started minus J1, I went end up at 0.5, I have to add 1.5. Y'all follow me? And that's impedance. Correct, class? Now, what element would have a positive J.1.5 possibility? A inductor. That's it. So if I think about this, my first element is an inductor, if I do it this way. And now inductive reactance is J omega L normalized by Z0, and that has to be equal to J 1.5. That means the inductance I'm going to get, L, is equal to 1.5 times Z naught divided by 2 pi F, and that was 3 gigahertz, right? Is that right or not?
Yes.
Times 3 times 10 to the 9. So Z naught for this one is 50. Put in 50. What do you get from this?
3.98 nanometers.
By the way, when you're talking about, wait a second, yeah. Oof, boy, that's small inductor. I'm telling you, that starts to make me, when you're getting around nanohenry values, the length of your leads can have probably, depends on, yeah, they can have nanohenries of inductance just in a lead length of 1.5 inches, 2 inches, I think. So you gotta be real careful with lead lengths when you're at those levels. And I mean, that is a small value. Millihenries is where I like to work. All right, but nanohenries is really small. All right, anyway, that's a theoretical value that I put in series with that. That's that inductor. So then what do? Now I go to the admittance domain, take 1 over that, and the real value better be 1. It looks like it's going to be, is it 1 minus J1?
Yeah.
That's a handy dandy thing. So now, went from there, that was 0.1, this is 0.2, this is 0.3, 1 minus J1, and now I'm in the admittance domain, and I want to add an admittance that's going to negate that J1, right? So it's in the admittance domain, it has positive admittance, the capacitor, right? The way I always do it, start the impedance of capacitor is 1 over J omega C, normalize it, it's 1 over J omega C Z naught. Then normalize the admittance 1 over that. So I figure out this capacitor by setting that C value here. So J omega C Z naught is equal to J1, or I can say that C is equal to 1 over omega, which is 2 pi times 3 times 10 to the 9th. Divide by Z naught, which is 50. And that gives me my value of C.
1.06 pico.
Is that right, class? So that's one solution, picofarads. But obviously you see the other possibilities, right? We could land here, have a smaller value of L, right? And then go up here, and we'd have another value of L. Y'all follow me in that class? Because you could land here and here, which means you could land either here in the admittance domain or here. And if I'm up here, and I'm adding admittance that's positive, that would be negative, that would be an inductor. All right. It's 14 after. I didn't get to my lecture material, but I'm not worried that much about it. I'm worried about making sure you understand this. We kind of did quite a few problems. I hope that it comes the light shine and you're understanding what I'm doing and why I'm doing it. So let me just, before we break up, tell you where we're going. All right, the next thing I'm going to do is S parameters. This is section 10.3. They're called scattering parameters, or S or 2-port parameters. And I'll tell you, this is pretty important stuff. Almost every kind of any high frequency equipment you use, network analyzers especially, they get what are called the 2-port parameters, the S parameters. And they're extremely important in analyzing a circuit in a high frequency domain and really understanding it, how it behaves. And I'm going to talk about that. I'm going to show you how to do it, what it means, and I have had some fair amount of personal experience with these things because of some of the projects that I've been involved in. And I'll tell you some of the tricks on this stuff, some of the things that would help. Y'all understand this lecture? And thank you for recording it. I hope the people who missed it have an opportunity to look at that recording. We're missing